All right, well, thank you everyone for joining us today. This talk is titled IPv666 Address of the Beast. And I'm Mark, and this is Chris.
Hello. So my name is Chris Grayson. I'm originally from Atlanta. I've been a research scientist with DARPA. I was the head of the Georgia Tech Hacking Club. Have also done penetration testing, both as like a full-time job and also a side gig. I had an attack surface enumeration company that went under. Turns out being an entrepreneur is difficult. And then most recently headed up the red team at Snapchat, and then left that for greener pastures at Bird Rides, where I am on the security engineer there.
Yeah, I work with Chris at Bird Rides. I've done a lot of work in the wireless security space, a lot of wireless reverse engineering and vulnerability research. I do DARPA challenges in my spare time. So I've done the Shredder Challenge, which was reassembling shredded documents. I did the first Spectrum Challenge in 2013 and 14, and I'm currently competing in the Spectrum Collaboration Challenge, which is their software-defined radio grand challenge. And so if the track name and the title of the talk wasn't self-evident, we're going to answer this question of what are we talking about? And we're talking about the future. And if you didn't know this, Chris and I recently visited the future, and we brought back this footage, and it's full of these rocket-powered water jetpack things that are pretty terrible. But we also found in the future a lot of IPv6 addresses. So we're going to start with some background on our interests for doing this IPv6 research. We're going to talk about some of the problems of scanning the IPv6 address space, namely it's huge. We're going to go through the different methodologies we tried for discovering IPv6 addresses. Some worked, some didn't work. Then we'll look at some results from the latest iteration of our tool set, which is called IPv666. Then we'll conclude with a bit of Q&A. So for some background, this is a graph of the percentage of Google users who have connected to Google using an IPv6 address. This is spanning a decade. On the left here, we have very little traffic starting to pick up in 2013 and 14. And by now in 2019, we have over 1/4 of the Google traffic is being served over IPv6. And this is just a single company. This is, may not extrapolate out to the entire internet, but this is a good indication that IPv6 is becoming more and more prevalent and is something that's getting more and more on our radar. So we got interested in this space through a vulnerability research project we took on in 2017 with our friend Logan Lamb. And we found a bunch of vulnerabilities in Comcast equipment. So this was cable modems and set-top boxes. And as part of this, a number of the vulnerabilities we found were pretty severe, but only exploitable if you knew the IPv6 address of the target device you were trying to attack. And so this is our first hint that discovering IPv6 addresses would have some pretty interesting security implications. And so for a little bit more depth, we have this one vulnerability here, which is my favorite attack chain from this project called send to TV. So send to TV is a Comcast service where you go to xfinity.com/send2tv, you put in a URL, and it shows up on your TV. And the way this works, your set-top box renders everything that you see in a web browser. And so you put this URL in, it loads that in the web browser on your set-top box on your TV. Now also, Comcast has cable modems, of course. And so you have multiple IPv6 addresses on your modem. Some of them are internet routable, and one of the IPv6 addresses is only routable from certain protected Comcast network segments. And what we discovered is that the set-top box is living in one of these protected network segments. So we were able to put in the IPv6 address of another Comcast customer's modem into this service. And because we were in that protected network segment on the set-top box, we could actually bring up the administrative web user interface of the target customer's modem on our TV and then log in with hard-coded credentials. And this was pretty bad, but we had the realization that this is only as bad as it is easy to discover these IPv6 addresses. And so we got interested in really trying to dig in and understand a little bit more about IPv6. And I want to preface this by saying we're not network engineers. I only learned how to read an IPv6 address about 1.5 years ago, and we're actively learning. So if we get anything wrong, please correct us. We look forward to that. And we wanted to start to understand IPv6 and look at some of the things that had potential security implications to us. So one thing that can start us right off the way is that the automatic configuration of IPv6 is such that if you have a device that speaks IPv6, plug it into an IPv6-enabled network, it will automatically configure itself and route to the internet if possible. So we have the suspicion that we might have devices that are routing to the internet over IPv6 that haven't explicitly or intended to be configured that way. We also have this lack of private address space. We have NAT and PAT with IPv4. That's less so with IPv6, so we have more addresses that are inherently going to be publicly routable. We have a discovery we made is that we thought IP tables was IP tables for everything. And the discovery that IP6 tables is a separate binary was news to us, and so that was an indication that the general level of knowledge of IPv6 for security practitioners like us was not terribly high, and so getting more education about this was important. We can't just block ICMP like we can in general with IPv4. And then we're also interested in this ability to potentially relay IPv6 packets to lots and lots of hosts. So we know we need to find some IPv6 addresses, and we discovered that there were some publicly available data sets, but in general, being able to discover new addresses was going to be key to identifying devices that had potential security vulnerabilities. And with IPv4, this is relatively easy. We have a 4.3 billion address space. That's a lot of addresses, but you can still port scan a single port across the entire IPv4 space in an afternoon. With IPv6, we have this huge number of addresses, 13 commas, no idea how to pronounce this, but it's very infeasible to actually try and brute force scan this space. Then we have the problem of the entropy introduced with the privacy extensions for Slack. So the way this works, with classic Slack, you have your MAC address, which is transformed into the host bits of the IPv6 address. If you connect to a website from your home and then from a coffee shop, you have two different IPv6 addresses, but your host bits are the same. So the privacy extensions for Slack introduces pseudo-random entropy so that you have a different set of host bits for each IP address that you have. And the problem is, even with a small network like a /96, that's still 32 bits of entropy, and it's something where it's unlikely that we're going to randomly guess addresses or use modeling to generate addresses that are using pslack. So now we're breaking this down into two separate problems. We have the problem of identifying pslack hosts and the problem of identifying non-pslack hosts. So for the pslack case, we decided to try some honeypotting, which had some success, some not so much. So we set up a server. We're running a DNS server, SMTP server, and a web server. And the intention was we would have users connect to this website and use this as a way to start collecting their IPv6 addresses. And we used this service called pop ads to generate some of the traffic. So pop ads is this completely legitimate ad network where you pay them money, and they have real users with real browsers and real computers connect to your website. And we selected pop ads because
there are real computers. I just don't know if they're they know that they're connecting to it.
Exactly. So we set up a blind DNS server on this cloud instance. We had glue records pointing to IPv6, and then we had some what we thought at the time was some fancy logic to try and redirect all traffic from IPv4 to IPv6. What we discovered after the fact is that if a device can speak IPv6, it will prefer it and will do so, and so that was all unnecessary. And here we have a graph of the DNS queries over time over the course of the year. And so we have a few spikes correlating with the pop ads campaigns we ran, and then a bit of a long tail of some remnant organic traffic, but not a huge amount of traffic. And so with pop ads, this is a graph of a 90-second window of requests coming in from a pop ads campaign. And we gave them $20 or something, and then within 2 minutes, they had sent approximately 50,000 requests to our website. And so it's an effective way to get independent, distinct IP addresses to connect to you, but they're not actual users. And one of the common referring URLs we saw was this page, which is a very legitimate website, which had an anchor tag pointing to our website. Then it had a Bitcoin crypto miner. And so we're suspecting that it may not be legitimate traffic.
And that was literally it. It was body, crypto miner, anchor tag, and no indication as to how that anchor tag might have gotten clicked, which is fairly interesting in and of itself.
Yeah, and then this led us to this web browser called CockCock, which we think is doing Facebook credential harvesting, and it's a whole other rabbit hole. So we set up this honeypot web server at IPv6.exposed, and we had this serving over both IPv4 and IPv6. We had images serving only over IPv6, and our thought there was that if people hit the website over IPv4, we could still get IPv6 requests, but again, that was unnecessary because every machine which loaded anything over IPv6 only talked to us over IPv6.
Yeah, we're kind of stubborn, so the main way we learn is through empirical testing.
And we fail a lot and iterate slowly.
Exactly.
And then we had a WebRTC payload on there, which would give us the potential local IPv4 address of the browser, as well as one or more of the IPv6 addresses. So here we have some graphs on the top. This is access log hits from the web server, and then we have postbacks from the WebRTC payload down below. And so we can see on the top, we're on the scale of tens of thousands and only on the scale of thousands below. And this told us that while we were getting traffic from these pop ads campaigns, only a small subset of the requests were actually loading the WebRTC payload and executing that. So this was another indication that the quality of traffic from pop ads wasn't very high and wasn't actual browsers loading these things in all cases. So then we set up a honeypot SMTP server. And this was kind of ill-conceived, but we had the idea that we would have individual machines connecting to this SMTP server if we could get on a bunch of spam lists and so forth. And in the end, of course, that did not happen. And all we got was some Hotmail infrastructure and Yahoo Mail infrastructure hitting our SMTP server. And so the SMTP server honeypot was kind of bunk. So after a year of doing this honeypotting, we spent, in the end, more like $1,000 or $1,200.
Yeah, emphasis on the plus sign.
And we got 92,000 unique IP addresses. And for our first attempt at doing this kind of discovery, we were happy that we got some. And then we went to do a connect scan or port scan of these to see how many hosts were live and what they look like. And then we learned about ephemeral IPv6 addresses. And most of these clients from the pop ads campaigns were actually hitting us with ephemeral IPv6 addresses. So we went back to do port scans or ICMP ping scans of these. Most of them were offline because they were ephemeral addresses. So we then had this realization that we're going to have to look at some other techniques because our year and expensive honeypotting techniques was completely wasted.
Yeah, and I think it's a good hallmark of a research project that you spend a bunch of money and waste a bunch of time for absolutely no reason. Really is an informative process. So that's how we were looking at the cryptographic randomness that we were trying to deal with in these addresses. And as far as we have found thus far, there's not really much we can do on that end because like the one way that we thought of to do this was going to be honeypotting, and honeypotting like. So, and just to further elaborate on those ephemeral addresses, it's the same sort of idea that you have with ephemeral ports now, where like an outbound connection just picks a random port that doesn't actually have anything listening on it. So if you're the server and you're receiving the connection from a client and they have an IPv6 address, that might not even be an address for their interface. It might just be something completely random within the network that they're on, that they're listening to. So we kind of just shelved that and we're like, all right, let's look at addresses that are allocated via other means, whether that's DHCP, static configuration, or non-PSLAC. So these are IPv6 addresses if you've never seen them before. And if you kind of cross your eyes a little bit, you might see a bit of structure in there. You'll see kind of like common byte boundaries that are used for network iteration. You'll see a number of patterns with like where the kind of expansion bits go. But like we're looking at these addresses and like these, A, humans are creatures of habit. B, this looks like there's a lot of structure in there. I wonder if we could have something learn that structure and then guess new addresses. And so what does any self-respecting computer science-based person do when you're trying to solve a problem like that? Obviously, you use machine learning. Because it's the solution to all problems. And so not only are we not network engineers, we are also not machine learning experts. So this was rather difficult. So I'm going to explain this in a similar way that it was explained to me, and I'm probably going to mess it up in doing so. But if you think about the way the human eye works, if you have like 20/20 vision or nothing's messed up with your lens, then the light rays that you are observing go through the lens, flip over, hit the back of your eye, and then it registers as your vision. And you get, with good vision, you have a fairly perfect recreation of what you're actually looking at. And then as your vision degrades, the quality of that image degrades. So you get like an error rate effectively. So what you are doing with these machine learning autoencoders, as they're called, is you're trying to create a lens that you can project data through, and you're trying to create a lens that has an error threshold, or basically an error percentage. And what's really cool about these lenses is that the error is actually going to be indicative of the structure of the data that you trained the model on. So the idea is you build a model, the model is imperfect, but the model learns a lot about the structure of the data that you're putting into it. Then you take a list of IPv6 addresses, pass it through the lens. Because the lens is not perfect, it basically transforms that data into a new data set. But because of the way that it is broken, it transforms it into a data set that is novel and representative of the structure of the underlying data. So that's what we were told. But so we might not be machine learning experts, but we are really good at making perfect lenses. Because no matter like how few weights or how like we tried finagling, and we even kind of employed the help of one of our friends who is a machine learning expert and didn't even figure it out. So I feel better about it. But basically, we created a perfect lens every time. So we would take like, okay, we're going to take our 10 million addresses, pass them through this lens, and it would just give us back the exact same addresses, which was really not helpful as far as we were concerned. So one kind of like common thing we like to do is get really dumb about things. One of my favorite sayings is, if it's stupid and it works, it still works. So we were like, okay, we can't do machine learning. Let's just get something out the door. So we came up with a really dumb probability model, with this paper coming to us as kind of some encouragement that we were at least heading in the right direction. So this entropy IP paper, I highly recommend looking at it. It's from a group of folks associated with Akamai. And they had this, like, I believe, absolutely massive data set that they're working with on the order of billions of IPv6 addresses. And they did this analysis of entropy breakdown within the addresses, which is what you see here. So left to right on the top here is bit position. And then the blue line is showing you how much entropy they observe in those addresses. So it makes sense that you see much more entropy on the right-hand side, because that's going to be the host bits. When you're using pslack, those are the bits that are going to be generated using cryptographic entropy. But this at least told us that we were in the right direction, and this whole like perfect lens thing was a PEBCAC user error, and that we should at least keep going. So we came up with this really simple and stupid way to do things. So here's the way it works. We would take an IPv6 address, and we would break it down into 32 nibbles. And what we wanted to do was create a probability distribution on a per nibble basis of what we've seen in our input data set. So basically, we would go through and say, okay, at position 0, when it's the value of OX2, we've seen the value of OX8 as the next nibble one more time. And then position 1, with the value of OX8, we've seen the next value of OX0 one more time. And we go through every single one of the addresses that we have, and then we have a probability distribution for every position for the current nibble value. Here's what we've seen in the past around all the data that we've ingested. And this, it kind of works, but one of the things that this doesn't do, that the entropy IP paper really kind of emphasizes, is you only have causality between adjacent nibbles, whereas you actually tend to have causality much further away in IPv6 addresses, especially considering, like, let's say that you have a network operator that is allocating at like the 32-bit boundary, and then has some addressing scheme that they're using for the hosts within it. So you actually have causality much further away than just adjacent. But it worked to some extent. So when we were using this model to generate new addresses, this is what we would do. We would start with OX2, because that's going to be the publicly allocated address ranges. We would say, okay, in position 0 with value of OX2, what is the probability distribution for the following nibble? So we say, okay, here's the different weights. We take these weights, we create a weighted die, we roll the die, and that gives us the value for the next nibble. And then we say, okay, then for position 1, value of OXA, what's the probability distribution for the next nibble? Do that for all 32. Now we have an address. Do that however many times you want to generate however many addresses you want. And so it turns out that stupidity is regularly awarded because this worked. And at first we thought it looked really well. Another kind of like tip with research projects, when you see results that look really, really good, hold off on your excitement because it's too much of a roller coaster otherwise. So this first time we generated 10 million addresses, and we did ICMP ping scan across all of them, and like 50,000 of them responded. And we were just like, wow, we really solved this problem. That was way easier than I thought it would be, but we're pretty great at this apparently. And then you're just thinking like, I don't know, that feels too good to be true. And that's when we discovered these guys. And to this day, I still don't really understand what the purpose of these things are, but they're alias network ranges. And what this is basically an entire network range. Every single IP address is mapped to a single host. So when you ping scan the range, every single host appears to be live, but it's actually all the same machine. And we're not talking about like small networks. We're talking about like a /32. We're talking about like hundreds of billions of addresses all pointing to the same one. So it turns out that when you have a feedback loop between your prediction model and the addresses that you find, and you start finding these addresses, your model very quickly trains itself to be completely useless because it only finds like these bad network ranges that we really don't care about, because it's like for every network range we found one machine, like yay. So this is a gigantic pain, and we had to figure out how to deal with it. And so here was a solution that we came up with. So let's say that we did a ping scan, and this IPv6 address responds and says, hey, yeah, I'm real. We say, hold on, you're not tricking us like that again. We got to figure this out. So we first wrap it in a /96. We have been told that we should wrap this in a /64 because of the way that address ranges are allocated. We have not made that change yet. But we say, okay, we're going to wrap you in a /96 network, and then we're going to just generate 8 random addresses within that network, right? So it's 8 addresses out of 4.3 billion. And then we're going to do an ICMP scan of all of those. And we say, hey, if 50% of those addresses respond, then we're pretty sure the /96 is at least aliased, right? Because what are the chances that you're going to guess 8 random addresses out of 4.3 billion and 4 of them are actually going to be live hosts? I don't feel particularly confident that I can do that. So if we say, okay, it is aliased, now the next step is to find the actual network boundary for where it's aliased at. So we would take this address, and we would map it to the bits. And we say, okay, we know the rightmost 32 bits are within the alias network, but the other 96 bits we don't know about yet. And so we want to do a binary search. So again, because every single address in these ranges are going to respond, if we flip every bit within that network range, then it should respond as well. And so that's the logic here. So we take the right half of the bits that we don't know about, and we flip them all, and then we do an ICMP scan. And then that results in one of two things happening. Either no response is received, in which case we know that the boundary for the alias network must be somewhere within the bits that we flipped, otherwise it would have responded. So in this case, we know that the bits that we didn't flip are clearly not in the alias network range, and the bits that we did, the boundary is somewhere within there. And if we do receive a response, it's the opposite, because the bits that we flipped are within the alias network range, and the ones to the left of them are not. So now we've narrowed down the bits that we don't know about to half, and we do this again, and it takes about 5 to 6 iterations for us to actually find the boundary. And it turns out that this works pretty well. And that was the state of our project up to the release of version 0.1. That is something that we released back in November. We've given another talk since then on this topic, and our second release that went with that talk focused on packaging things up in a way that was really easy to install. And so for this release, which is version 0.3, this is our general mantra in life, but also the main mantra behind what we wanted to contribute for this release, because we don't like giving the same talk twice. So we wanted to get better. We wanted to get a better probability model for finding addresses, and then we wanted to be able to search around the address space that we found addresses in, which is what Mark is going to talk about next. So this is another really interesting paper published in 2017 out of UC Berkeley, and I highly recommend reading it. It's got an algorithm within it that is entitled 6gen, and it's a pretty in-depth analysis and a lot of really good contributions around how we should think about the problem. Also, another kind of side note: if you're ever reading a paper and there's a section that's like, here's the algorithm, and then it's immediately followed by, here's how you can optimize the algorithm to actually get it to run, it's probably not something you're going to be able to package into a tool all that easily because it's very expensive to run. Another thing that we learned. Oh, we left that transition in there. Wonderful. The biggest contribution in my mind, or at least to the work that we did that came out of this paper, was their notion of what a cluster in IPv6 address space is. And so they define a cluster as an IP address and a set of wildcard nibble indices. So you have an IP address, you break it down into 32 nibbles, and then you say, here are the nibbles that are wildcards. And what a wildcard nibble means is that for an IP address to be contained within a cluster, all of the nibbles have to match, but if it's a wildcard in that position, it can be any nibble. So I'll elaborate on that a little bit in a second. But in order to measure kind of like how good a cluster is, we think about two things, capacity and density. So capacity is how many IP addresses can we have within this cluster? And then density is of that number of IP addresses, how many of them are from the data set that you built the cluster off of. So if we have a cluster of size 16 and 8 of those IP addresses are from the data set that we're building this model off of, then it has a density of 50%. So just to show a bit of an example, here's our same friendly IP address that we looked at before. We would take this and we would create a cluster of size 1 out of it, which is fairly uninteresting because at this point, there's no wildcard indices. It's effectively just an IP address. But then if we said, okay, we want to expand this cluster out to include a second IP address of our choosing, represented by this one right here, we take the second IP address, we break it down into the nibbles, and then we say, how many nibbles actually line up? In this case, for this example, there's only one offset where there's a difference, which is right here. So the question then becomes, okay, what sort of transformation do we have to do to this cluster so that it includes both of these IP addresses now? And in this case, we would now have a wildcard in that index, or at that index. So in this case, the capacity would be 16 because we have one wildcard, which can have 16 different values. If these are the only two data points that we have in the data set we're building the cluster off of, then it's got a capacity or a captured of 2, which means it has a density of 12.5%. And just kind of to hammer this home, here's the 16 possible values in that cluster, right? All the nibbles are held common, or held constant, except for the ones in the position where we have a wildcard, and that is the cluster. And so going back to what I was saying before about the causality between different areas or different offsets within an IPv6 address, this really maps that well, because you can say, okay, well, here's the nibbles that they're commonly iterating on over here and also over here, and they can be entirely separate parts of the address, which I really liked about this idea. So with that in mind, let me tell you about the original algorithm, the algorithm put forth in that paper. So first, we're going to take every single IPv6 address that we have, and we create a cluster from every single one. Every single cluster is of size 1. It has a single IP address in it, and that's where we start from. And then we say, okay, for every cluster that I have, I'm going to look at what it takes to create a cluster with every other one at a time, right? So this cluster and this IP address over here, what are the wildcard indices that I would need to add to create a cluster that contains both of them? And then once I have this cluster, I say, how good is this cluster compared to all the data that I've got? So you're basically evaluating the density of the cluster given I'm taking this one and adding it to it. And then for all of this, for every cluster, you're trying to find the best upgrade candidate. So of all the transformations that you can make, which one gives you the best density? And then you take all of those upgrades and you sort them by density in reverse. So now we have a list of clusters that we consider to be our model, and then we have a list of upgrade candidates that we're choosing from that are sorted with density at the top. And then we have this notion of a scanning budget. And the kind of the intuition behind the scanning budget is maybe I only want to send like 10 million ICMP probe packets. So my scanning budget is 10 million. And the idea here is that we're going to continue to grow the cluster set until the cumulative capacity of all the clusters within it exceeds 10 million. Because then we can scan every single possible address in every single one of these clusters. So while the scanning budget is not exhausted, we take the best upgrade off the top, move it into our model, and then recalculate what the next upgrade, the next best upgrade for that cluster could be, right? So we're iterating on potential upgrades for things that we're introducing into our model. It's a really cool idea. And the prowess that was made in this paper, cannot be understated. It works really well. But the problem for us was, like, right off the bat, the data set that we're working with is about 15 million IP addresses long. So you immediately get X squared because you're taking every IP address, creating a cluster, and then checking it against every other IP address. And then if you don't do this well, and if you don't have specialized data structures for this, it turns into X cubed. Because then, once you have this cluster, you have to see how many of your input data set actually fall within it. So you're having to analyze your entire data set again. So you don't do it right, it can be X cubed off the bat. This scanning budget didn't really map to what we wanted to do. We're trying to get to a point where we can give you like an Nmap-esque experience for IPv6. So, and also the cluster model is being built with the intention that like you're going to scan everything in it, which is like, okay, cool. Like have this tool go scan this bunch of IP addresses that we already had and like have fun. We didn't really know how we were going to make use of that. And again, this evaluation, same sort of evaluation as up top. If you don't do it right, it can be expensive as well. So I wrote code that ran this algorithm, and then I'm just like sitting there watching the log output thinking like, well, I should have paid more attention to the section of the paper that was like, here's the optimizations you can make. And lastly, this is not intended to identify new addresses. So if you really grok like the idea behind what is trying to be accomplished here, it's we want to find, you have like a budget of scanning that you want to do. We want to find super dense clusters, or at least the densest clusters from your input data set. And then we have the ability to scan every possible address within them. In that case, it's kind of like you're finding these bounds around your data that have a high probability of like the missing holes that you don't have yet are worth scanning, which for the purpose of the paper sounds great, but it wasn't intended to be like, we're going to generate new addresses we've never seen before and find them. So we added 2 6s to the name of the algorithm and dumbed it down, as we're pretty good at doing. And so here's the way that we do it. So we start in roughly the same way. Every single IP address, we have a cluster of size 1 for it. But instead of then going back and analyzing it against every IP address that we have, we just say, okay, there's 32 offsets that we can pick wildcards at. Let's see what each one of those choices gives us. And so it's only x times 32. That also gives us the ability to identify when a cluster has no good upgrade options. If the constraint is you only get to add 1 wildcard at a time, and if every addition gives you the same density, it means that none of the wildcards that you add are actually capturing any additional IP addresses in your data set, meaning that this IP address is just kind of out there in the ether, not all that closely related to any of your other addresses. So we then take all the ones that don't have any good upgrade candidates and remove them. From there, we sort upgrades by density, and then instead of having a scanning budget, we have a scoring system. And we score based on density, the total capacity, so how big the cumulative size is, and then also number of clusters within the cluster set. Because if we can have the fewest clusters with the biggest size and the best density, that seems intuitively where we want to go. And so this, like I said before, reduces the complexity by a decent margin. And then again, when we're actually removing all those IP addresses that don't have any nearby neighbors, this gets rid of like 80 to 90% of the addresses that we have in our data set. And we don't throw them away. When I talk about what we use those for, it might make more sense. So there's no scanning budget. So we continue to improve a model. Basically, so long as the score of the model that continues to grow, we continue to iterate on it. But then as soon as it like kind of falls down, then we say, okay, this is as good as the model is going to get, and then we're happy. But one thing that I haven't talked about yet that is still expensive is deduplication. So when we pick a new upgrade to move over to our model, there is a chance that that new cluster entirely contains other clusters that we have, at which point we need to be removing the clusters that are already contained by it. We don't want to count them twice. And that's actually fairly expensive. So we pick kind of a step size, and we say, like right now for the model that we have packaged up in master, we take 25,000 upgrade candidates and then evaluate, and then look at the score. And then if everything's good, we take another 25,000. So we're not having to recalculate or do this deduplication every single time we pick an upgrade. So once we have that model, we then move to the problem of what do we do with this model to actually predict new IP addresses. And so what we do is we first pick a cluster out of the cluster set at random. And then for every nibble that we need to generate, we have a like probability threshold. Right now in master, it's 10%. So 10% of the time, it is going to pick a nibble from the probability distribution that we've seen in all of those ones we didn't include in the model at random. So basically, all of the stuff that did not make it into the clusters that we have in our model, we have a per nibble probability distribution. So if we were choosing to pick from that model, we'd say, okay, at this position, what is the distribution of nibbles that we've seen? And we create a weighted die from that, roll it, and that's the value that we go with. The other 90% of the time, we generate it from the cluster. And if we're generating from the cluster, it's simpler logic. If it's a wildcard, you roll a 16-sided die, and that gives you what value you want. If it's not a wildcard, you're just taking the nibble value directly from that cluster. And so now Mark is going to talk about what we do in relation to expanding out our search from individual IP addresses.
So after we've done this generation and discovery step and we've found some new IPv6 addresses that are associated with live hosts, we want to take advantage of the fact that there may be either neighboring addresses in sequential order or other addresses with small nibble changes to the initial address that might be valid as well. And so we fan out using these two techniques. We start with the nibble adjacent fan out. The premise here is that we've discovered an address, so this bottom address is the example address we've discovered. We have a target network that we are scanning, and we vary each nibble in the newly discovered address and generate 15 new addresses for each nibble that is not part of the network mask. So this network mask is a /4, so the first nibble, that first 2 in the address is fixed, but we can vary every other nibble in the address. This gives us up to 465 new candidate addresses for each discovered address. So we start by setting the 31st or 32nd nibble to 0, and then 2 because we have one in the original address, and we go down and we've created now 15 new candidate addresses based on this starting address. And then we do the same for all of the nibbles that are not included in the network mask. And this actually proves to be pretty effective because we have a lot of addresses which have different nibble variations from what we've actually discovered. And this gives us approximately an order of magnitude more addresses than we get just from doing the 666 gen discovery step. Then we also do a /64 sequential fan out. The premise here is that if we discover any : 1/64 addresses, so this is an address where the right 64 bits are 1, and the left 64 bits are the /64 network bits, we monotonically increase the network bits and also monotonically decrease the network bits. So we generate neighboring /64 networks. And so in this case, we're taking that left 64 bits and going up and down. And by default now, we generate 1,000 /64 networks on each side of one we've discovered. And then we do a similar step for identifying hosts within these networks. The idea here is that people can manually configure devices with monotonically increasing addresses, or if they're using DHCP with monotonically increasing addresses, we might have addresses that are sequentially up from these /64s we've discovered. So by default, we generate the first 500 hosts within each /64 that we've seen, and then scan for those. And with the sequential fan out along with the nibble adjacent fan out, we're getting a considerably larger number of addresses now than we had with our previous implementation. And so the question we want to ask ourselves is us smarter? Have we improved? Have we learned from this? And so version 2, version 0.2, which we released at ShmooCon.
You're pretty proud of.
And yes, it was pretty good. We were running this for 8 days, and we discovered 58,838 new addresses. 80% of these were not in public data sets, so we're able to demonstrate that we can generate tens of thousands of addresses that are novel. Now, we've made a few improvements for this version 0.3 release, and it's been pretty remarkable. So we ran a scan this morning for 1 hour with the current implementation and our current model, and we discovered 1.57 million new IPv6 or live IPv6 addresses, 78% of which were not in any of our existing data sets. So this gives us approximately 1.2 million live IPv6 hosts we discovered in 1 hour. This was throttled to 50 megabits per second on a DigitalOcean cloud instance.
This is also more of a testament to how comically bad we were before to how great we are now. But we got this number like earlier today, so this is still kind of sinking in that this actually works.
Yeah, we didn't expect it to be this good.
So we're I don't know. I feel it's like reasonably happy to have a 500,000% improvement.
Yeah, it's all right. And so we took a sampling of 100,000 of these addresses that we generated this morning and did TCP connect scans for some common ports. And we wanted to sanity check ourselves and make sure, are these actual live hosts? Are we just crazy? And we had some pretty good response. So a lot of SSH and telnet services, a lot of web services. There are a lot of networking equipment, and this is both infrastructure networking equipment as well as consumer premises equipment, so cable modems, that sort of thing. Lots of ancient SSH and telnet servers, some no-auth Mongo instances, lots of Windows RPC, all kinds of things. And so this is good validation of the fact that our generated data set is in fact internet-connected live hosts with network services running on them. And this is really promising because if we've been able to generate this set of 1.57 million in an hour, we can quickly start to amass a pretty good set of novel IPv6 addresses.
And one thing that is kind of interesting about this, so going back to the comment that I had about how ICMP-v6, or that Mark had about ICMP-v6 being a critical protocol now. So there was one day that Mark's sitting at his apartment, I'm sitting at mine, and he was able to ping my Chromecast from his network, right? Wasn't able to, so it could also ping my laptop, could ping all the devices on my network, but could only do TCP connect scans to, I don't even think you could do it to my modem. No, so could still get the pings through, but TCP, UDP were being correctly firewalled off. So that will be another kind of interesting iteration of this work is, with how much we're able to see via ICMP, what can we then do with it? I believe that the ICMP v6 parsing stack in Linux is new, or well, not new, but is not the same as ICMP. So if there are any sort of memory corruption exploits or vulnerabilities that could target that, I think they probably have a pretty wide reach. So anyways, our tool set is called IPv666. As I said before, our 0.2 release, which had a bunch of feedback from HD Moore, so many thanks to him, was like, hey, this tool's cool, but you should package it up so it's not a gigantic pain to install. So now, if you have Golang 1.11 or greater on a machine, this is all you have to do, and then so long as gopath/bin is in your path, then you can just run it. It also has its ICMP scanning built in. It only supports Linux right now. We don't really have any plans to put on anything else because it's apparently a gigantic pain to get these sort of like guaranteed speed throughputs across different operating systems. But yeah, please give it a whirl, see what you think. As I said before, 0.3 we focused on candidate address generation and then discovery. So we had the new model, as well as once we find initial landing points, we kind of start a search around that space. We still have plenty of other things we'd like to add, but we're pretty happy with it at this point. So there's 7 different utilities that come packaged with the tool. The first one is the one that I think would probably be the most interesting to folks here, and that's just the discovery scan that we've been talking about this whole time, where like literally if you do go get blah, and you can just do IPv6 scan discover, it will start, and it will start going across the global address space. We have scan alias, so if there's a particular IPv6 range that you're looking at that you want to see, is this IPv6 range aliased or not? It's a way to basically, it carves out that one little kind of alias detection thing so you can target it at one specific network. Generated addresses, I think this is another one that people might be interested in. Again, pull it down, IPv6, generate addresses, and then give it an output file path, and it'll generate 10 million addresses and write it to that file path based on the model that we package up with it. If you want to generate your own model, we have that utility as well. If you have a big list of IPv6 addresses, you can throw it at this. It is memory hog. So on my MacBook Pro that has like 16 gigs of memory, I cannot build a model with all 15 million addresses. I have to remove a bunch of stuff. I can do it with about 9.5 mil. So if you have a big beefy memory box, then like it'll probably work just fine. But also the model that we were talking about before that has given us millions of addresses since this morning came from 9.8 million addresses. Oh, and actually one thing that's kind of cool about that is we see a fall off to some extent with how many addresses it can find on a per model basis. So like we're kind of conceptually thinking of it as we're building this model around all these clusters, and you have this kind of like dense crust around these clusters of IP addresses that haven't been seen before. And once you exhaust that crust, kind of your hit rate goes down considerably. So we built another model this morning with more addresses, and then ran scanning on it, and then checked to see like, hey, is there much overlap in the addresses that these two models are finding? And there was like less than 0.5% overlap.
Yeah, so it suggests that we can continually generate new models as the existing ones get exhausted, and hopefully continue this process iteratively.
Yeah. So generate blacklist. Yeah, if you have IP addresses that you don't want to scan, you can throw IPv6 CIDR ranges to this tool, and it will add them to the blacklist that it doesn't scan. Clean will take a list of IPv6 addresses and remove all the addresses in it from the blacklist that is either packaged up or the one that has been added to through your use of the tool. And then convert is kind of a tool that we use mostly for converting files of IPv6 addresses from one format to another, whether it's text or binary or hex. Here's Zelda and some links. And then we'll wrap it up with a conclusion.
So just to wrap up, we started with some background on our interest for getting into this space and some of the things we tried with varying degrees of success for discovering addresses. And finally, we decided to be less dumb, and that worked out pretty well. We've shown that we're able to generate a significant amount of previously unseen to us IPv6 addresses with live hosts. Then we have our tool set IPv666, and we encourage you all to take a look at it. And now we have time for some Q&A. And here are a few links we'll leave up for a minute of some related work, which we definitely recommend taking a look at.
Do you want to show what the current count is up to?
We're
not on the
not on the
internet.
internet.
Okay.
Yeah. So we've had this running. So we were at 1.57 million after the first hour. After the second hour, we were at 2.6 million, and we last checked after say 4 hours in and about 5 million addresses. So it's just humming along.
So yeah, so from like the entire, so we went to as many different places as we could to get public IPv6 data sets. And we did this about a year ago now, so I'm sure a bunch of it is outdated. I bet there's more out there. But the corpus that we're building off of is 15 million large. And in the span of 4 hours, we've been able to get a third of the way there with completely new addresses that we haven't seen before.